Alright, so here we go. We're going to do chapter 4, part 1 of chapter 4. Just want to let you know that I know that this is not the best thing, but it's the next best thing to being there. It's not live, it's not Memorex, but it's the next best thing. So we're going to go to chapter 4, open your slides up. I'm going to begin on slide 2, talking about the concept of pressure. Pressure is the force per unit area. It is measured in millibars typically. There are other measurements, but millibars are what we are using in class for the most part. Sea level pressure is approximately 1,000 millibars, and total pressure is defined by Dalton's law, where you can measure the partial gases, the partial pressure of all individual gases to total the pressures, to sum the pressures. And pressure is not exerted in just one direction, it is exerted in all directions. If you look at 3 different containers, the container on the left, next slide, shows just a sealed container. But if I increase the density of the molecules inside, I increase the pressure. And then on the third, if I increase the temperature, I also increase the pressure. It's in the ideal gas law. This next slide is pressure decreases with altitude. Recording stations are at different altitudes all over the world, and so we have to normalize them all and make them look like they're at sea level. Errors are introduced, so we have to correct those errors. Compressibility of the atmosphere gases results in non-uniform decrease of pressure. It's non-uniform, as the next slide 5 indicates. Pressure does not decrease with height in a uniform rate. Alright. Next slide is we have an equation of state, which is called the ideal gas law, where you have pressure, temperature, and density. They're all related to each other. They have a relationship with each other, and it is mathematical. If you have constant temperature, an increase in air density will cause pressure to increase. If you have constant density, an increase in temperature will cause an increase in pressure. Okay. Then next we show you that we measure pressure typically by using a mercury barometer. We use from that we call it barometric pressure. Just a column of the mercury. If it increases, the air pressure is higher. If it decreases, the air pressure is lower. Simple. Slide 8 is a picture of one. Number 9 shows you the corrections that we have to make. We have to correct for elevation, for air temperature, and for gravity. Okay. And then next we have alternative ways of measuring barometric pressure called aneroid barometers. It involves a little more work, but it draws out a graph for you in slide 11. You have to calibrate them every single time you use them. So they're a little more cumbersome. Slide 12, we have maps now, weather maps, that distribute the air pressure. All of those lines, each one of those lines are called isobars. Each one of those lines represents one pressure amount. Say 1,000 millibars, which is sea level pressure. Say 1,012 millibars, etc., etc. Each one of them represents one of those. Okay? Steep pressure gradients, which means if you put a bunch of those contours or isobars together, you have a steep pressure gradient, which shows a quicker or more rapid change of pressure. It could be up, it could be down, downward pressure. But the steeper the pressure gradients, the closer the isobars are to each other. The weaker the pressure gradient, the wider spaced, the more widely spaced the isobars are. Those are all. That was the weather map in 1994, March 4th, as a matter of fact. So next slide, 13, we talk about pressure gradient a little bit more. Uh, it's wind. The direction of the pressure gradient is wind. Okay? And the pressure gradient force is the strength of that wind. When we talk about pressure gradient force, we're really talking about horizontal wind speed, moving from left to right, east to west, north to south, horizontally. Alright? Typically, the pressure gradients are fairly weak in large areas, but on occasion we might have a tornado, a hurricane, etc., where the pressure gradients are very strong in a very local, small area. But let's talk about vertical pressure as well. In vertical pressure, it's quite the opposite. The pressure gradients decrease. Okay. Well, what I'm trying to say is it's opposite. Vertical pressure decreases as you increase in altitude. Horizontal pressure gradients decrease as you decrease. I'm sorry. Always decrease with increasing altitude. Okay, that's the point of that bottom bullet. Always decrease with increasing altitude. Alright. But the vertical pressure gradients are always more intense, more extreme. Okay. Slide 14. Hydrostatic equilibrium what all that means is that we always try to achieve equilibrium in the atmosphere. Even though there's uneven distribution, it's always establishing equilibrium. So, density plays a large role in hydrostatic equilibrium. Gravitational force is proportional to the mass. A dense atmosphere needs greater gravitational force to remain in balance. Warm air, for warm air, this equates to smaller vertical pressure gradients. For cold air, this equates to larger vertical pressure gradients. Moving on to the next slide, this causes a density decrease. When you heat, the density decreases in the column of air. And it contains the same amount of air, but it has lower density to compensate for its greater height. So we're just expanding or contracting, one or the other. Next slide. Regarding horizontal pressure gradient in the upper atmosphere, it's best determined through the heights of the constant pressure due to density considerations. So you try to find constant pressure, and then you determine the pressure gradient at that time in order to find the direction of the wind. We'll get to that. We'll just coax you through that slower. It's going to be a lot clearer real soon here. But notice the bottom bullet. The height contours indicate the pressure gradient. So that's the most important part. Alright. Just turns out to be arrows on the map. Next slide, 17. The Coriolis force is almost a magical or imaginary force, but it has to do with the Earth rotating, and as the mountains start moving through the air mass causes, the atmosphere above to be turbulent. It starts to twist it, makes it circle, and the influence results in deflective forces causing two types of motion, vertical, horizontal, but they work together. They cause a rotation, if you will, of the pressure. Overall, you see a right rotation, if you will, in the northern hemisphere, and a left rotation in the southern hemisphere. Okay. The deflective force in slide 18, it increases with speed. Alright? It moves from, it doesn't have much of a force. Coriolis force is virtually nil at the equator, but it's maximized at the poles. But it also increases with speed of the moving object. Alright. And then we show you some instances pictorially, graphically. Slide 19 in your book goes farther regarding the Coriolis force affecting the speed and the direction of the wind. Yes. Then we also have the ground that causes friction, slows it down. Okay, so friction reduces wind speed. So when the Coriolis force is over land, it is slowed down faster than it is over water. But the friction that we're talking about is generally, rule of thumb, at the surface to about it's affected about from the surface of the earth to about 1 mile up. Anything above 1 mile is free atmosphere, we say. It's, in other words, friction does not really have much of an effect on the atmosphere. So anything above 1 mile, which is 5,280 feet or 1.5 kilometers, is frictionless. It's above the planetary boundary layer. So when we're talking about the Coriolis force, it's everything 1 mile and below. So your airplanes fly above the planetary boundary layer. You know, go on and on and on. I could about that. But let's move to slide 21, and then we will take a break right about here. Let's take a break, and we'll pick up on the second part of 2 parts for chapter 4.